Okay, so welcome everybody. So I just announced the last homework assignment for this class. So one last problem from chapter 4 and 2 problems from chapter 5. And it's due 2 weeks from now on April 4th. So today, after learning all the stuff that we did, we're going to start talking about black holes. And what I want to do with black holes, well, that's chapter 5 in the book. And what I want to do is I'll start with the sort of most elementary properties of black holes. So I'll go through the elementary solutions, the one that we know and like, Schwarzschild, Raison, and Nordstrom, and Kerr. And then what I'll do is to extract from that really the most crucial properties of black holes and the most general properties of black holes, and in fact go through that again in a way that doesn't require a lot of knowledge about very specific solutions. So there's a lot of properties about black holes that can be extracted, can be discussed without ever writing down a metric. We just look at the most essential properties of the black hole solutions that we know and basically generalize them to more general black holes, and that will basically be the bulk of my discussion in this part of the course. And part of what I want to do, the ultimate achievement, is going to be a discussion of the laws of black hole mechanics. Those fourth laws that are closely analogous to the laws of thermodynamics. So we'll talk quite a bit about that. And now we have at our disposal all the tools that are required for a thorough discussion of these things. So all the stuff that we learned, going back to congruences, hypersurfaces, and now the mass definitions and angular momentum definitions that we discussed earlier on in the course, well, now all of this will be applied, all of this will be put together, and we'll be able to do a lot of meaningful things around black holes because we have now all the techniques that are required for that. So the basic story of black holes, I think, is familiar. So just to draw a picture, I'm going to draw a space-time diagram where time goes upwards as usual, and space goes sideways. And the first thing we need to do to have a black hole is to have gravitational collapse. So we're going to start with a star that's going to be starting from some finite radius, presumably, was stable for most of its lifetime. It started out as a static configuration, and then all of a sudden it collapses because, for example, of the disappearance of radiative pressure when all the nuclear burning is stopped. So we start with a nice, static star, and at some point it starts imploding. And what we learn in GR is that once implosion is started, well, if you're not going to form a black hole, you can stop implosion by invoking either, atomic forces in the case of white dwarfs or nuclear forces in the case of neutron stars. But if the mass of the star is too large, then none of this succeeds at stopping implosion. And once implosion has proceeded beyond the event horizon, nothing will stop implosion, and implosion will continue until, basically you reach a state of all the matter concentrated into a point, infinite densities, and that's what we call the singularity. So after implosion to zero volume, we get the formation of a singularity that persists, after the implosion has stopped. Of course, this is a classical description, and we sort of know that this is limited because, well, the state of infinite density presumably doesn't make sense. There's probably something more compelling that occurs beyond the classical description. If we want to understand what the singularity really means, we have to go beyond the classical description. We know that this is a place where GR breaks down, and presumably that's the realm of quantum gravity, and it's still the hope that quantum gravity will tell us exactly how to describe the singularity in a more meaningful way. But at this stage, we still don't know what it is, so we still continue to call it a singularity. We'll still say that it corresponds to a state of infinite density, even though we don't really know what that means. I mean, it's sort of ridiculous to think that, the mass of the sun could be concentrated into a mathematical point. Clearly, that doesn't make any sense. Clearly, Heisenberg uncertainty will have to come into play at some point so that you cannot, really specify that the volume of that, infinite concentration is really zero. So presumably there's a finite extent. Presumably there's a more meaningful way of describing the singularity. But at the level of the classical GR description, we're sort of stuck, and we have to say that, yes, it does proceed all the way down to r equals 0. So the rest of the story has to do with how light rays behave in a spacetime produced by gravitational collapse. If you're very early on in the collapse, gravity is weak and light rays are only very weakly affected. So light rays emitted early would just go out from the center, and of course, there's some scattering events taking place inside the matter, but we won't worry about this. At the level of this cartoon, we can imagine that light rays, emitted from the center will just keep going unaltered all the way to infinity. So that's a very weak gravitational interaction between light rays and the matter, because at this point, gravity, the matter is still diffuse and gravity is still very weak. Very late, so a little bit later in the collapse, gravity becomes stronger because the star has become more compact during collapse, and now we find that, the main manifestation of gravity is to delay light rays, so light rays emitted later will take more time to reach a given observer at infinity, or, at some safe distance. So light rays are being delayed, so they take longer to reach destination. And ultimately, after the collapse has proceeded beyond the event horizon, we find that light rays don't even make it to infinity. So a light ray emitted here will be caught by the gravitational pull of the star and will be forced to recollapse into the singularity. So light rays emitted very late don't even make it. They just stay captured by the gravity. And then there's this limiting case where a light ray emitted from the center at just the right time during the gravitational collapse would be caught in between those two behaviors. It can't make it to infinity, but gravity is not yet strong enough to pull the light ray back. So that light ray has no option but to just stay there, stay put at r equals 2m. And that's basically the definition of the event horizon. It's that surface beyond which light cannot escape. And that horizon is defined by stationary light rays that are maintained in place by the gravitational pull of the black hole. So that's the formation of the event horizon. In the future of the event horizon, all light rays are captured. In the past of the event horizon, light rays can escape, but it takes longer and longer to get to a finite observer at a finite distance. And just before the horizon is crossed, just before the horizon is formed, a light ray emitted just before would take a really, really long time to make it to infinity. So that's the notion that an observer looking at the gravitational collapse proceeding would see the star never quite making it to the event horizon, because everything would be delayed. And ultimately, as the star is just about to cross the event horizon, the last signal coming from that event would never make it to the observer. So as the observer looks on, it looks as if the star is, collapsing more and more slowly, and it never quite reaches the event horizon. That's just basically an artifact of the fact that the observer has to observe this collapse through the emission of light rays, and those light rays take longer and longer to get there, and therefore the observer will perceive the collapse as being, slowing down, and never quite making it to the black hole stage. There's more to the story than that, because as the observer looks at those signals propagating outward, it's not just that they perceive a delay, they also perceive a redshift. So those light rays emitted early, of course, are not strongly redshifted, so we can ignore this. But as gravity becomes stronger here and especially here, that gravitational redshift becomes extreme, and in the end, the redshift becomes infinite. So light rays not only take longer to get to the observer, they also get more and more redshifted. And in fact, as this thing proceeds in time, the redshift goes exponential. So before the observer sees the slowing down taking place, they see a fading of the signal. They see a fading of the signal in intensity, and they say, of course, they also see the wavelength becoming longer and longer. So in fact, they stop with a detector of a finite finite band. They will stop seeing the radiation coming out well before the star has crossed the event horizon, because of the delay, because of the redshift, and because of the fading in intensity. All of this come together. So basically, the actual picture that an observer would see is one where they see a fainter and fainter signal coming from a redder and redder object, and eventually the wavelength just escapes the ability for the observer to detect it, and that's basically what gravitational collapse would see from a finite distance. So the stationary surface, of course, is known to be at r equals 2m. We know that this corresponds to the event horizon of the black hole, and we know that anything that happens beyond r equals 2m is forever hidden from external observers, because, for example, any event that might occur here, if you wanted to manifest, if this event wanted to manifest itself to external observers, it would have to emit light. But that light, even though it would try to go outwards for a while, would be captured by the gravitational field, and that light would eventually be rejoining with the singularity. So light emitted outwards might behave like this. Light emitted inwards will behave like this. So anything that happens inside the event horizon will never be perceptible, will never be measured, will never be seen by observers outside. In a picture like this, it's important to recognize that the light cones are not straight. So the light cones are tilting as we approach the event horizon. So incoming light rays will always behave simply in a diagram like this. Incoming light rays are blue shifted to some extent by the gravity of the star, but that blue shift effect is not nearly as important as the redshift effect that takes place around the event horizon. So it's a finite blue shift instead of being an infinite redshift, so we don't need to worry too much about this. And in this picture, incoming light rays will basically behave almost on a straight line. So they'll behave like this, like that, and like this. So if you want to draw light cones, well, you just take an incoming light ray, an outgoing light ray, and you build a cone out of this. So far away from the black hole, the light cones look nice and straight like this with two edges at 45 degrees. But as you go nearer the black hole, around here, for example, the light rays tilt inward. And that just means that observers that are forced to move within the light cone are increasingly unable to escape the gravitational pull of the black hole. Here, there's still a little bit of a window of opportunity. But once you're inside the black hole, that window has disappeared. And if you're inside the black hole, you have to travel within the light cone. And once you're inside, there's no escape. You have to hit the singularity sooner or later. You can fight it all you want. All you can do is to delay it a little bit. But ultimately, if you fall inside the event horizon, you will meet the singularity, which is an unpleasant event for anyone who's tried it. So I think this picture is is sort of very familiar. And what I like about this cartoon is that it really conveys all the essential points about black hole physics. So you see the gravitational collapse, you see the behavior of light rays, you see what the horizon corresponds to, you see the light cones, and basically, ultimately, there's very little need for anything else, right? So we could be happy as physicists talking about black holes at a cartoon level like this, and I think we would have all the main conceptual points, taken care of. Of course, we want to do calculations, so ultimately we have to write down the metric, we have to do calculations, we have to verify that this cartoon picture is borne out by the actual, metric of black holes and the behavior of particles and light rays in that. So we have to make this all, more quantitative, but we won't learn an awful lot more than what we have here. So it's just that we can codify it and make it more quantitative. So the prototypical black hole is the one that lives in spherical symmetry. So for a non-rotating black hole, we have automatically a Schwarzschild black hole described by the Schwarzschild solution. So that's probably the best known and simplest solution to the field equations. And I like to write it this way. And f is the metric function, and that's the thing that goes to 0 at the event horizon, and that's also the place where the coordinate system seems to be in difficulty, because when f is equal to 0, we lose the coefficient in front of dt squared. The coefficient in front of dr squared is becoming infinite. So something is happening there that needs to be cured. But I think the difficulties of the coordinate system, I think, are also familiar to you guys. But I'll still talk a little bit about that. Yep.
By non-rotating, do you mean that aspect of the space is not rotating?
That's right, no rotation, period.
So it's like a spherical symmetry thing.
Well, so I want to talk about this because you can have a non-rotating object that's not spherical, right? So it could be a cube, it could be any shaped object that's non-rotating. If you were, so let me backtrack and I'll answer your question. But by non-rotating, I mean that the object that's collapsing has no net angular momentum. Right. So we could still devise an object that would have, shells rotating this way, compensated by shells rotating the opposite way. So just a whole succession of counter-rotating shells like this. If there's no net angular momentum, the object as a whole is not rotating. And a collapsing object like this will form a Schwarzschild black hole. So two comments that will relate to your question. So there's two famous theorems that relate to the Schwarzschild spacetime. The one is Birkhoff, that says that if you have vacuum plus spherical symmetry, then the result is Schwarzschild. That is, the theorem states that if you have a vacuum solution to the field equations in spherical symmetry, that solution must be the Schwarzschild solution. So I give you at least some attempt of a proof of this in the book. The remarkable aspect of this is that there's no statement about the fact that the spacetime has to be static. So the spacetime, in fact, in the non-vacuum portion of the spacetime, we could have a lot of dynamics. We could have a pulsating star, for example. But anywhere outside of the star where you're in vacuum, there's no sign of that time dependence. There's no knowledge of this. The metric outside must be the Schwarzschild metric. That's true in GR. It's true also in Newtonian gravity. If you had a pulsating star in Newtonian gravity, the Newtonian potential inside the star would be varying with time. But the potential outside would be the usual Gm over R. And basically, we find the same story here. The metric inside a pulsating star would be time dependent, obviously. But the vacuum metric outside of that star would actually be the Schwarzschild metric. And that carries no time dependence whatsoever. So whatever is time dependent inside has no impact on the external aspect of the gravitational field. Physically, that's just a way of saying that a spherically symmetric system can be time dependent, but that time but it emits no gravitational wave. So there's no gravitational wave that would correspond to a spherical activity, to a spherically symmetric time dependent process. That produces no gravitational waves because it would correspond to a time-dependent monopole moment inside the star. And to get a gravitational wave, you need a time-dependent quadrupole moment. A monopole doesn't do it, the dipole doesn't do it, but you need a quadrupole, a time-dependent quadrupole moment to get any gravitational wave. So you can have a time dependence inside, but that time dependence doesn't propagate as a gravitational wave outside, and you've got your Schwarzschild solution. That's Birkhoff's theorem. There's also a uniqueness theorem that's due to Werner Israel, who was my PhD advisor. That goes back to the late 60s, that says that if you have a non-rotating object plus an event horizon, then the result is again Schwarzschild. So that statement is very different. So for Birkhoff's theorem, we don't care whether or not there's an event horizon present. But we care about the fact that we impose spherical symmetry. In the case of the uniqueness theorem for black holes, the Israel theorem, the point is that we don't impose spherical symmetry. We could have a collapse that proceeds from a highly non-spherical state, which would be the case, for example, for any normal star that starts collapsing under its own weight. A star will never be a perfect sphere. It will always have some deformations corresponding to, for example, the presence of magnetic fields that would create, shape distortions and various things like that. We rule out rotation here, so we're not talking about, a rotational deformation. But even a non-rotating star will have some, imperfections to it. It will never be in a pure spherical state. Nevertheless, what Israel's theorem says is that if you have a non-rotating object that collapses beyond an event horizon, what emerges in the steady state, in the stationary aftermath of the gravitational collapse is a Schwarzschild solution. So spherical symmetry is not imposed, it's a result. You get a perfectly spherical spacetime even though the initial state was not spherical at all. That's a very remarkable theorem that was very much unexpected and surprising when it was first announced. That was back in 1967. I was 2 years old, so I don't have a vivid memory of it. But the interpretation of this was pretty tricky, because suppose that you start with this highly non-spherical object. For example, you start with a cube. So you have a star that's in the shape of a cube. I know it doesn't exist, but nevertheless, the theorem will say that the cube will collapse and leave behind a perfectly round, spherically symmetric Schwarzschild black hole behind. So now the question is, well, first of all, can this happen? Second of all, how does it happen? One loophole that the uniqueness theorem leaves out is the fact that, well, you require your final spacetime to have an event horizon. Not only that, it has to be a smooth, regular event horizon where you don't find any curvature singularities or anything like that. So one option that was considered at the time is that, well, that maybe the black hole state is just too simple, too special, that the cube will in fact not collapse all the way down to a black hole, or it will create, some kind of highly singular object that would be, not a Schwarzschild object, not a black hole. So that was one possibility, but when people started to do perturbations of spherical symmetry, they realized that, those perturbations, in fact, did give, a perturbed so if you do a gravitational collapse of a spherical body that has a small perturbation on it, people discovered that the perturbation would eventually decay away, and the outcome would be a result where the perturbation is completely absent, and the final outcome is a Schwarzschild black hole. So there seemed to be no sign that even, that at least in a perturbed sense, in a perturbation approach, that the object would create singularities, that the collapse would create singularities before a horizon is encountered. The other option is that, well, as was suggested by perturbative analyses, that what really does happen is that anything that's non-spherical about the body as it starts collapsing becomes a whole set of multiple moments that become time-dependent because of the collapse. So as soon as you have a non-spherical object that collapses, you have an object that has, a set of multiple moments, and all those multiple moments now depend on time because of the dynamics of the collapse. If you have time-dependent multiple moments starting at the quadrupole, you have the possibility of emitting gravitational radiation. And what people understood after a few years of thought and calculation was that, well, that's exactly the mechanism to allow a relaxation to a spherical state. All of those higher multiple moments that become dynamical start to produce radiation. A lot of that radiation escapes out to infinity. Some of the radiation is actually captured back by the black hole, so it bounces off the, the space-time curvature. It backscatters, it collapses along with the body. And in the end, after this radiative process, you find a very nice relaxation to a black hole. Through basically the emission of quasi-normal modes and a relaxation, beyond that, that eventually produces a nice stationary state, produces a Schwarzschild black hole. So that was the remarkable sort of, understanding that came after the uniqueness theorem. It's not just that you can have black holes, but those black holes are much simpler than the original objects. The original object could be shaped arbitrarily. The final black hole, if you don't have rotation, will be a Schwarzschild black hole. Spherical symmetry will be resulting from the collapse. So the bottom line is that black holes are much simpler than macroscopic bodies. To describe a macroscopic body in complete detail, you have to provide a lot of details. You have to provide the exact description of the shape. You have to provide the exact description of the density profile. You have to provide all the internal structure. You have to provide all those details. For a black hole, that's it. They're all the same. They all look like this. They all have the same metric. The only thing that differs from black hole to black hole is the mass. But all Schwarzschild black holes, whatever the mass, are described by a spherically symmetric spacetime with this very simple metric. That's the simplest version of the no-hair theorem, and there's an extension to this that applies to Kerr black hole. That was the generalization of Israel's theorem by Brennan Carter and others that showed that all those statements can be generalized to a rotating state. And now, instead of relaxation to a Schwarzschild state, you have relaxation to a Kerr black hole. You had a question?
For one thing, does the state become a stationary state? Does this always happen in a finite amount of time?
Yep, it happens pretty fast, actually. So as the thing starts collapsing, it starts emitting radiation. So part of that radiation just follows light rays out to infinity. Part of that radiation backscatters in. But all of this, collapse itself proceeds under, a fluid dynamical time scale, which is extremely short. The settling down to a Schwarzschild state, basically happens over a time scale corresponding to the gravitational time scale of the space-time, which is set by the mass. So if you're dealing with the collapse of a one solar mass body, the length scale associated with that is 1.5 kilometer. That's the radius of that's the unit of length that corresponds to a one solar mass. The time unit corresponding to that is a microsecond. So the time unit corresponding to the mass is a microsecond. All processes taking place outside the black hole basically get done over one of those gravitational timescales. So everything is over in seconds. So the relaxation is very fast. I mean, the relaxation in quasi-normal modes is very fast. And then there's a further relaxation that takes a little bit longer. But that is basically done, within, again, a very, very short time after the collapse. Other questions about?
Are these coming from numerical relativity, or do you
have? A lot of studies. So a lot of that was based initially on perturbation theory, because that's the only thing that people could do at the time. So the study of quasi-normal modes and things like that, radiative processes around black holes. But that's certainly confirmed by numerical relativity now. So people can now routinely produce gravitational collapse, away from spherical symmetry and see what happens. And while typically they do it with rotation because it's hard to prevent rotation from taking place, but they see a relaxation to a Kerr state that occurs very, very fast. So even in highly non-perturbative situations, that's certainly seen to happen. And there's still some assumptions, known as cosmic censorship. So all of this relies on the known or the presumed formation of an event horizon. But if you have an event horizon, then I think the body of knowledge and the body of, the rigor that's attached to that body of knowledge is very high. So I think that's very firm knowledge. All right, other questions? So that's basically the general view of black holes now, that basically the black hole state is very, very simple. That's true for Schwarzschild, certainly, and that's going to be true for Kerr. Especially when you compare with the macroscopic body that preceded it. So the star that preceded it was extraordinarily complicated by contrast, because if you want to describe a star fully, it's not enough to specify 2 or 3 numbers. You have to specify a whole collection of functions that will describe the density profile, the pressure profile, the temperature profile, all of those things inside the star. So that's an extraordinary amount of detail. Whereas for the Schwarzschild black hole, well, once you know the mass, you know everything, and you can write down the metric on one line, and that's a much, much, much simpler description. So the good news about black holes is that they're really much simpler than anything else we've seen in nature, and that's why, well, that's why so much work could be done around black holes, because they're really very simple. Okay. So when we look at the Schwarzschild metric, typically we look at it in this coordinate system involving a time coordinate t and a radial coordinate r. And we know that something strange goes on at r equals 2m in the metric. And for a good 40 years, people didn't understand what was going on there. So Schwarzschild came up with the metric in 1916. And there were pockets of understanding that were soon forgotten in the years between 1916 and 1950 something, 58, even 1960. And it's only when people started to look at black holes more seriously, after there was a real need to incorporate them into astrophysics, after the discovery of quasars and all that, that I think the understanding of that coordinate singularity became full. So, so historically, so basically, no one was working in general relativity from 1917 on to 1960. I mean, that's a oversimplification. There were some schools. Einstein continued to work on GR to some extent, not an awful lot. There were a school of Einstein collaborators like Peter Bergman, who worked on quantum gravity. There were people like Nathan Rosen and various collaborators of Einstein who were were working on the problem of motion. But by and large, from the 20s on to the 60s, there was very, very little activity in GR. It was a deserted area. I mean, there was an appreciation for GR as a beautiful theory that was completely useless and divorced from any practical applications. That was the reputation that we had back in those days. And there was a major revival in the 60s, basically because of the discovery of quasars and high energy phenomena in astrophysics. It's only then that people understood that, well, to explain these things, you had to have sources of energy, and gravity was an excellent source of high energy. And then a lot of people flooded back to the field in order to flesh out the properties of black holes and see if they were really viable in astrophysics. And that led to the golden age in the 1960s and 70s and so on. So during this sort of low watermark, as it's been called by historians, people were looking at the Schwarzschild metric and noticed the problem at r equals 2m, and they tended to dismiss it because they said, well, this needs to apply to normal stars. Normal stars are much larger than 1 kilometer, and therefore you never have to worry about what used to be called the Schwarzschild singularity at r equals 2m. Gravitational collapse was not considered, and people knew that, of course, the Schwarzschild solution only applies to the vacuum exterior. If you want to describe the matter interior of the star, you have to do something else, and therefore r equals 2m is not really part of the domain of validity of the Schwarzschild solution. So anyway, so those difficulties were basically pushed aside. No one recognized. I mean, very few people recognized the importance. Although, as I said, once in a while you saw a paper coming out saying that, well, there potentially could be a problem with r equals 2m if you had a highly condensed objects, and here's a possible solution. And there was a pocket of people, in the 20s and in the 30s who analyzed this and provided a solution. But because no one was interested, no one paid attention, and those, people like Painlevé on Goldstrand and Robertson and various people like this, no one paid any attention. So back in the 60s, all of that work had been forgotten and was only rediscovered later. And it's only in the 60s where people really started to pay attention to this again. And because there was a need for black holes, there was really a need to understand what goes on at r equals 2m, and a need in particular to understand what was going on with the coordinates there. And the basic difficulty of the coordinates is that, well, we're writing the Schwarzschild metric in terms of a coordinate t that really makes sense out at infinity. I mean, it's a coordinate that's really attached to how observers at infinity measure time. Because a major requirement of working out the Schwarzschild solution is to say that we want to have asymptotic flatness. And at infinity, when r goes to infinity, we want that metric to reproduce the Minkowski metric at infinity, with the usual interpretation for t, r, and the angular coordinates. And in particular, t is supposed to mean, well, time as measured by Lorentz observers, inertial observers out at infinity. So when we do our Schwarzschild metric, derive the Schwarzschild solution, well, we incorporate that condition, and implicitly we decide that we're going to be working in terms of a t-coordinate that's really suited to external observers. And the problem is that that t-coordinate is not suitable to observers that may follow the collapse and fall inside the black hole. And that's the dichotomy that I explained before. So we know that light rays take an infinite time to reach the observer as the event horizon is crossed. And therefore, if I were to describe the motion of an observer falling inside the black hole in this way, I would find that, well, the motion of that observer in terms of that t would seem to take an infinite time. But that's really just an artifact of the fact that I'm really describing the observer as, it's really because I'm picking time to describe the motion of the observer, and time is really attached to measurements that would be made by an observer at infinity. And those measurements have to be related to each other. Events on the falling observer's events on the falling observer's world line and observations at infinity have to be related by light rays. And if it's true that my light rays take an infinite time to reach the observer, well, it's going to be true that as measured by t, the motion seems to proceed in an infinite time. The problem is easily recognizable. Then it's an easy diagnostic. If t is not suited to the measurements that the observer himself would make or herself would make, maybe it would be better to choose a different time coordinate that would be better behaved in terms of the measurements of observers that would actually fall in. And one option would be to use proper time, proper time as measured by this observer, as a time coordinate to describe the Schwarzschild metric around the event horizon. And if you were to do that, you would find that the metric in terms of proper time would look like, would look perfectly regular across the event horizon. There would be no difficulty across r equals 2m. And the motion of the observer, of course, in terms of proper time, would proceed smoothly in finite time and all of this. So an option is to transform the metric in terms of proper time instead of this coordinate time that's associated with observers at a fair distance, at a large distance. And that is giving you basically the Painlevé-Goldstrand form of the metric that you've encountered in problem sets. So if you rewrite the metric in terms of proper time for observers falling in, you find that the metric becomes it's still a very simple metric, but now there's no apparent problems at r equals 2m. And that's one of my favorite coordinate systems to describe the Schwarzschild metric, but I won't discuss it in any detail. So it's pretty clear that the problem is with t. There's no problem with r because r always has a well-defined geometrical meaning in terms of areas of surfaces, surfaces of constant r and t. So there's no need to redefine r in our coordinate system, but there's a really strong need to redefine t. Another option to come up with a regular coordinate system is to tie the new coordinates to the behavior of light rays. And that's the idea behind the Eddington-Finkelstein coordinates. And that's my second favorite coordinate system to describe the metric, the Schwarzschild metric. And in fact, it's really my favorite. Painlevé-Goldstrand, I like its properties, but I don't like to work in it all that much because I find Eddington-Finkelstein is even simpler to work with. And I tend to choose that on top of everything else. So let me just spend a little time describing what these things are. So Eddington, of course, goes back to the 30s. He was one of the early relativists. Finkelstein is something that showed up in the 50s. And basically, probably, I forget the history there, but he probably rediscovered Eddington's work independently. So, and it's only after the fact that, it was realized that what he was doing was exactly what Eddington had done, a long time ago, but no one had noticed. So the idea is to design a new time coordinate by basically examining the behavior of light rays. And that's the start of a theme that we're going to keep on exploring a little bit. So it's typically a good idea to try to figure out what the light rays are doing in a given space-time, because the behavior of the light rays will tell you how things behave causally, what the causal relationships are between various events. And if you have a coordinate system in which the behavior of light rays is simple, then you have a simple way of mapping the space-time in very meaningful terms. So so what I'll be looking at here are radial light rays. And what I mean is that they only propagate in the radial direction. They don't propagate in the angular direction. So for those light rays, theta dot is going to be equal to 0, and phi dot is going to be equal to 0. So they only move with time, and they only move in the radial direction. So if we want to figure out what those light rays are doing, we go back to the metric, and we know that ds squared is going to be 0 along light rays. And by looking at the line element over there, we can actually see that it factorizes very nicely. We have a dt minus 1 over f dr that multiplies a dt plus 1 over f dr. So if you work it out, you find that, well, you get the dt squared, you get vanishing cross terms because they cancel out, and then you get the dr squared times 1 over f squared, but you multiply by f, and that gives back the f minus 1 dr squared that we had before. So one thing I can do, so this is a perfect differential, so I can call this du. This is another perfect differential, and I can call this dv. I can integrate these things, and u is going to be the is going to be t minus the integral of the r over f, and v is going to be t plus the integral of the r over f. Those integrals can be done. I'll just write it. This is r minus 2m log of r over 2m minus 1. And what we have at this stage is the statement that we get light rays when u is constant, so that du is 0, or when v is constant, or dv is 0. So u equal constant, that corresponds to, in the old coordinates, that corresponds to t increasing with r, so those correspond to outgoing light rays. And v equal constant corresponds to incoming light rays. So in the cartoon over there, those would be the u equal constant rays, and those would be the v equal constant rays. Okay. One option is to take this seriously and to say that we could rewrite the metric in terms of u and v. But that apparently doesn't solve anything because we still have an f in front, and something funny is still going on at r equals 2m. So in the old form, of course, now we know that, well, that the problem comes from t. So we still have a problem here, and we need to think a little bit in order to resolve it. One thing I can do is to take, so in order to just think about this, one thing I can do is to take the difference between u and v to get rid of t. If I take the difference between u and v, I get, I meant to do it the other way, v minus u. I get twice the integral, which is twice the expression that I wrote before. V minus u, yeah. And that's twice r plus minus 4m log r over 2m minus 1. So when r goes to 2m, we see that the log here goes to minus infinity. And that means that this is finite. That means that v minus u goes to plus infinity. Did I get this right? Let me just check the signs here. Oh, it's a plus. Yeah, okay. That was a plus sign. That was a plus sign, so it's really the other sign here. So when r goes to 2m, the log goes to minus infinity, and we find that v minus u goes to minus infinity. And that could mean, well, that could mean a couple of things. Either it means that v goes to minus infinity, or that u goes to plus infinity. V going to minus infinity means that you look at those incoming light rays and you look at what they were doing, you know, in the infinite past. I didn't say this quite right. Right, okay, so if we consider a sequence of v equal constant light rays, by going to minus infinity, it means that we're looking at a sequence of light rays, you know, that go toward the past, that goes into this direction. And that doesn't mean that doesn't seem to mean that we're actually approaching the event horizon. So, so the point is that this is probably not the cause of the difficulty. When we're looking at u goes to plus infinity, we're looking at light rays like this that are, you know, moving forward in sequence like this. And the point is this: so this last light ray over here is the one that's actually labeled by u equals infinity. So I'm not giving you a very compelling case here for one way or another, but the point is that if you look at this a little bit more closely and analyze the behavior of light rays, the point is that we still have a coordinate singularity here because u goes to infinity as we approach the event horizon. So we still have a problem of coordinates because our sequence of outgoing light rays basically accumulates up to the event horizon where u goes to infinity, but it doesn't proceed beyond that. We don't have, you know, the next, you know, set of light rays that follow the formation of the event horizon. Those are not captured by this this labeling of outgoing light rays. We would need to extend this beyond plus infinity to be able to capture those additional light rays. So we still have a coordinate singularity here because basically we still have geodesic incompleteness in our coordinate patch. We're not capturing all the geodesics that we would need to capture in order to have a smooth transition across the event horizon. So we'll come up with a way of curing this. I mean, there's a way of handling this that's pretty simple, and that gives rise to the cross-co coordinates. But before we do that, I'll just notice that, well, if this is really what's going on here, maybe what I can do is to pick v as a coordinate. Forget about u. I'll just focus on v. And if I focus on v and adopt v and r as coordinates, I'll have a perfectly fine metric to work with. And that's the idea behind the Eddington-Finkelstein coordinates. You just eliminate u because it doesn't, you know, it still gives you trouble, but you retain v, which is perfectly well behaved, and you keep v, you keep r, and you just rewrite the metric in this coordinate system. And now you have a perfectly regular metric, as will be seen in just a couple of lines of calculations. So Eddington-Finkelstein is really all about adopting v and r as coordinates. So we get rid of t, and we replace it by v. So here we just remember that dt is going to be given by dv minus 1 over f dr. We plug that inside the metric. We get minus f dt squared, which is dv minus 1 over f dr squared. We have f minus 1 dr squared, and then we get the rest of it. Going through with the calculation, we get minus f dv squared. And we get a cross term. The cross term comes with a minus sign. We get a 2, but the f's go away. And here we get that the dr squared term here and here cancel out. I really want them to cancel out.
At dB is plus wherever at R. Oh, sorry.
Sorry. Yeah. This should have been a plus anyway. Let's see, what did I screw up here? Oh, what if? Okay. Minus squared is plus, right? Okay, I seem to have forgotten that. I don't know what happened. Yeah. So the dr squared term do cancel out. So we get a minus sign here. We get a plus sign here. So there's no dr squared term. And we get our new metric in the new form, which looks like this. So now you're asking, okay, well, we still have an f in front of dv squared, so have we really fixed anything? And it turns out that, yes, we have. So this is, in fact, perfectly fine. But can I give you a good reason for it? Yeah. So the point is that there's really no issue with the f going to 0 or changing sign across the metric, because basically the additional terms in the metric, in particular the off-diagonal term, will change some things. So for one thing, here there's no obstacle in calculating a metric inverse. There's no obstacle in calculating a metric determinant. So in fact, this the change of sign here at r equals 2m is not an issue. It was an issue before, as we recognized, partly because, well, as this was changing sign, this was also changing sign, but in a much more violent way. So there was, certainly additional problems with this. Even if we lose a term in the metric at f equals 0, we still have enough there to actually still deal with. So we still have a well-defined metric, even though one of its coefficients goes to 0. And bottom line is that if you were to calculate the motion of geodesics, the motion of everything in that metric, you would find that everything is nice and regular. If you consider, so one problem that might arise, for example, is if you consider an r equal constant observer. For that observer, and suppose that theta and phi also are constant. For that observer, ds squared would be equal to minus f dv squared. And now you say, okay, maybe now there's a problem. Maybe there's evidence here that there's a problem. But what does it mean? R equal constant observer, either you're somewhere here, safe away from the black hole, in which case, the metric is perfectly fine. And in fact, that relationship would tell you the relationship between your proper time and the new coordinate time v. Right? There would be a factor of f. Now the question is, well, what if you're not, an R equal observer at f equals 0, at r equals 2m? Well, that means that you're up here. And if you're up here, you're not an ordinary observer. You have to be a light ray to be threading the event horizon. Right? And if you're a light ray, it has to be true that your proper time goes to 0, and that's exactly what this does. What happens if you're inside the black hole where f is negative? If you're inside and you're at an R equal constant, if you're an R equal constant observer inside the black hole, I'm not sure if I can draw this. Yeah, I mean, those would be surfaces like that. And don't try this at home because it's becoming overcrowded. The point is that for an observer like this, you would find that ds squared is actually positive. And the conclusion here is that, well, this would have to describe a space-like displacement, not a time-like displacement. And we knew that because we know that if you're an observer inside the black hole, you have to move this way. Inside the light cone, you have to be moving with r decreasing always. If you're inside the black hole, you have to move toward decreasing r. There's no option because you have to keep moving within the light cone, and that takes you closer and closer to the singularity. If you pretend to be moving this way, you're moving outside the light cone, which you can't do if you're a massive observer. So that's what we're learning by staring at the metric and recognizing the virtue of having a metric coefficient here that changes sign. It teaches us something quite important about the nature of R inside the black hole. R inside the black hole is no longer a spatial label. It's become a time label. An observer inside the black hole has to proceed with decreasing R. R has become basically a time label instead of a spatial label. All right? We'll circle around that some more times to make everything clear. But the point is that, well, you can take my word for it, in spite of this change of sign here, which we had before in the Schwarzschild metric, but it was more problematic at that time because of this simultaneous blow up of this metric coefficient here. Here, this change of sign is not a manifestation of a coordinate singularity. Those coordinates are perfectly regular, and they're perfectly regular because the sequence of light rays that we're talking about here, to which we assign a vehicle constant label, this sequence of light rays really has no problem as we move back and forth along the sequence. None of those light rays encounter any sort of difficulty approaching the horizon. There's no accumulation the way that we saw with the other set of light rays, because we have a coordinate system that's attached to those light rays, which are really smoothly extended across the event horizon. This coordinate system is perfectly well behaved. And to me, so whenever I work with black holes and I need, for example, to decide whether a quantity is well behaved at the horizon, what I always do is to switch to this coordinate system, because first of all, the coordinate transformation is very simple. It's just given by this here, or in integrated form, it's just given by t equals v minus r minus 2m log r over 2m minus 1. So it's very simple. It's a very simple coordinate transformation. The metric is still very simple to deal with, even though it's non-diagonal, but it's not a big deal to deal with off-diagonal terms. And I can work happily with this metric, with this coordinate system, and do whatever I want to do across the horizon. If I need to assess whether a quantity is regular across the horizon while working in terms of this coordinate system, will do the job. Maybe I'll just go through a quick example of this just to illustrate the power of this. Another virtue of the coordinate system is that everything is explicitly defined. So the old coordinate t is explicitly defined in terms of the new coordinate v. And I haven't given up r. When we do classical coordinates in just a few minutes, things get more complicated because, and this we see right away, if we were to work in terms of u and v as coordinates, well, first of all, we wouldn't be getting rid of the coordinate singularity as we saw, because we're still dealing with this accumulation that we see happening at the event horizon, so we don't cure the problem to begin with. But more than that, if we wanted to work in terms of u and v, we would get rid of r as a coordinate. R would become a function of u and v. And r is defined as a function in v through this relationship right here. And the problem, it's not a real problem, it's not a big problem, but it's an obstacle. R is only implicitly defined in terms of u and v. I cannot invert this relation to give me r as an explicit function of u and v, because I can't invert this function here when I have a log and a linear term in it. So this coordinate system is simpler than Kruskal, for example, which is a variation on that theme over there. It's simpler because we don't give up r as a coordinate, and r is very useful because it has this immediate geometrical meaning that we would be loath to lose if we were to lose it as a coordinate. Okay, just a small aside to just explain the power of the coordinate transformation. So for example, imagine yourself, you do a calculation in Schwarzschild, and you have the components of a vector field expressed in the original coordinate system. So you're given a vector field A alpha in t, r, theta, phi coordinates. So, for example, you may want to solve the Maxwell's equations for a vector potential for whatever source of electricity you might have in your space-time. And when you solve Maxwell's equations, well, you have to make sure that you satisfy the boundary conditions. You have to make sure that your potential falls off, appropriately at infinity, and you have to make sure that your potential is regular across the event horizon to have a valid solution to Maxwell's equation. But now the difficulty is, if you're given a vector field in terms of coordinates that are singular on the horizon, how are you supposed to recognize whether the vector field itself is a regular vector field? How are you supposed to recognize that if you express the vector field in a singular coordinate system? And the problem, the answer is that you can't. In order to recognize the regularity of a vector field, you have to use a well-defined coordinate system. You have to use a regular coordinate system, and make sure that the vector field is going to be regular in this coordinate system. And then you can see what consequences that poses, what conditions that implies for the vector field expressed in the original coordinate system. So we want to check regularity of the vector field at r equals 2m. And the problem is that we can't do this with a singular coordinate system. We have to adopt a coordinate system that's known to be smooth and regular. And so the procedure is to adopt a regular coordinate system. For example, v, r, theta, and phi. And basically impose that the components in this coordinate system be regular. And then you can see what conditions that implies in terms of the original coordinates. And then work out what are known as regularity conditions. So the way this works is, well, you just declare that the components of the vector field are going to be smooth functions of the coordinates. And if you have the components of a vector field in a smooth coordinate system all smooth, then you know that the vector field itself, as an abstract object in a space-time manifold, will be a smooth vector field. But typically what you would like to do is to say, okay, having imposed this, what conditions do we have on the components in the original coordinate system? Because ultimately it's simpler to work in the diagonal form of the metric, and you would like to impose the right conditions on the solutions you got in that form. Well, the answer is simple. You just translate. You translate and you just do the coordinate transformation. You say that the coordinates the coordinate, the components of the vector field in the old coordinates, in the tr theta phi coordinates, are going to be the old components times the usual factor that incorporates the coordinate transformation. So in particular, AT will have to be given in terms of AV times the derivative of t with respect to v, plus the derivative plus AR times the derivative of t with respect to r, and plus the other guys corresponding to the angular components. But there's no other term because, you know, t doesn't depend on the angular coordinates. But t here is understood as standing for a function of v and r. So we have to take the partial derivatives under this understanding here. So this guy here is going to be 1. And that guy over here is going to be minus 1 over f. And what you get from this is that AT will be something regular minus something singular. So you will find, of course, that corresponding to this is the statement, you know, along with this will be the statement that AR doesn't change because the radial coordinate has not changed. So the point is that AR, when you work in TR coordinates, AR itself will have to be a smooth quantity, a smooth function of the coordinates. But this thing here will have to incorporate a singularity in order for the vector field to be smooth. But that singularity is not an arbitrary singularity. It has to behave as 1 over f as you approach the event horizon, and the coefficient has to be tied to AR. And if you don't have, you know, if your solution for AT doesn't satisfy this property, then your solution will be, in fact, will fail to be singular. Will fail to be regular. In order to be regular, ironically speaking, you have to make that function of the singular coordinate systems as singular as this requires. So that's something that, you know, in my work from time to time I have to do. You know, I work out some, you know, some solution to Maxwell's equations around the black hole, or some solution for that matter to a gravitational perturbation around the black hole. I'm calculating gravitational waves. Well, when I impose my boundary conditions across the event horizon, I have to do this very carefully, because if I, you know, don't do the right thing and impose the right, you know, singularity behavior for my functions, I know that I will get the wrong solution. I will get, in fact, a singular solution, even though it looks as if here I'm incorporating a singularity into my solution. But it's required, it's necessary for the vector field itself as an abstract quantity in the manifold to be a smooth vector field. So that's very important. In the old literature, I mean, typically people, I mean, that's the sort of thing that people would make mistakes about. An example of this, I won't name names because I'm being taped, but so recently I did some work on calculating the tidal deformation of a black hole, and one thing I wanted to calculate is the tidal quadrupole moment of the black hole, you know, how much of a deformation the black hole has. And I did the calculation, and I got an answer, and then I found out that this calculation had been done before, back in the 80s, and I looked at that paper, and it had a different answer. So now, well, scratch my head. Does it mean that we're working, you know, in terms of a gauge, you know, dependent quantity? Does it mean that there's some ambiguity in the thing that I was trying to calculate? So scratch my head, and I conclude no, there's no ambiguity, and you know, and my answer should be the answer. And then I look at the old paper again, and I notice that, well, he was working a solution in terms of the original Schwarzschild coordinate system, and then I said, well, you know, surely he didn't, you know, fail to incorporate regularity conditions, but then I go and check that using my Eddington-Finkelstein coordinates, and sure enough, his solution was singular on the event horizon, which he had missed, and therefore his answer was wrong because it corresponded to a singular solution to his equations, as opposed to what it should have been, a regular solution. So, so it's not unusual when you go back into the literature that these sort of things were missed, and people, you know, people made mistakes based on the fact that imposing regularity conditions on solutions can be tricky when you're dealing with a singular coordinate system. So the fail-safe way to avoid this is to, go back to a regular coordinate system. This will always work, but then you have to pay the price of, having extra terms in your metric that are not perfectly diagonal. So you have to deal with off-diagonal terms, but in the end, that's really not a big deal, especially when you compare this with the safety that it gives you to work in that coordinate system. The other approach that people have taken is to, use cruscal coordinates, and there's a lot of merit to using cruscal coordinates. That's what I'll talk about just now. But cruscal coordinates are much harder to use. In fact, they're really clumsy to use because of this implicit relationship with R that we saw before. But there's some virtue to cruscal coordinates in that it really opens up the full structure of the Schwarzschild manifold in a way that this coordinate system over here doesn't allow you to do. For some purposes, this whole structure can be, I'll come back to that. I'll tell you what I mean later. But for most of my purposes, I never saw the need to go beyond this, and I found that to be perfectly adequate and, in fact, very convenient. But for some purposes, and we'll talk about that briefly, to go full-blown and go to the cruscal route, can be very instructive. Okay, let's talk about cruscal just briefly before we break for lunch. We're back here. So we're going to go back to the idea of maybe trying to write down the metric in terms of our two coordinates that are tied to the behavior of light rays. So things that are called null coordinates. So we're back to this context over here of radial light rays. We're going to make a first attempt to introduce null coordinates in this way, tied to the behavior of light rays. We're going to make a first attempt to rewrite the metric in terms of those two coordinates. And we're going to see that, well, in terms of those two new coordinates, u and v, we have r defined implicitly as a function, and that that introduces some practical difficulties, but no difficulties of principle. But one issue that we encountered, and now we would have to tackle, is the fact that, well, we still have this accumulation problem going on. Those light rays that I'm talking about are labeled by u, and u accumulates to infinity as I consider the sequence of light rays accumulating up to the event horizon, and it doesn't allow me to go beyond the event horizon, and therefore I'm not capturing all of my space-time with this coordinate patch, which is not unusual. I mean, it's very frequent that coordinate patches capture a portion of the space-time, but not all of it. For example, the initial Schwarzschild patch only covered also the external part of the space-time. It didn't capture the interior, but the Eddington-Finkelstein form does capture the interior as well. Okay, so what do we do about that? Well, we can think of a function. So instead of u and v, we can think of redefining. So we do basically coordinate redefinitions. We're going to introduce a new u that's going to be, an uppercase u as a function of little u. And we're going to introduce a new v that's going to be some function of little v. So we can always do this. That doesn't spoil any of the properties we've introduced before, because, in fact, any function of u will be constant on outgoing light rays. Any function of v will be constant on incoming light rays. So this property that the coordinates will be tied to light rays is preserved by just doing those coordinate redefinitions. But maybe we have a choice, maybe we have a chance now of killing this problem, because all we would have to do is to invent a function that stays finite when the argument goes to infinity. And there's tons of functions you can invent, and probably the simplest one is an exponential. And that's what Kruskal did. So that was back in the late 60s, late 50s, early 60s, where people were playing around with, coordinate difficulties. And Kruskal just realized that if he were to define capital U to be just minus the exponential of minus u. And while v is not an issue, so v he could have, v could have kept the same as before. So the new v could have been the same as the old v, and that would not have spoiled anything. But just to include more symmetry into this construction, little v, big V was defined to be this function of little v. And, well, you see what happens, right? So as u goes to plus infinity, the exponential goes to 0, and there's a chance that u might be extendable to negative values. And that was the idea, so that now you introduce a new labeling for those light rays, a labeling in terms of plus u, and plus u would be negative outside. It would accumulate to 0 at the event horizon, but then you can continue u, big U, and it will take positive values inside the event horizon. So that's what the construction achieves, and the way that you recognize, excuse me, the way that you recognize that is that you go back to the metric. I didn't tell you what kappa was. Kappa was 1 over 4m. You go back to the metric, you make the substitutions, and you find that after doing this and replacing the du here by d capital U and dv here by d big V, you find that the 0 in f is going to be compensated by the 0 that occurs in u, because when you calculate the differential here, u will appear in the denominator, or the exponential factor will appear in the denominator. So this 0 will cancel out that 0 over here, and you've picked kappa here to be appropriate, so that after using L'Hospital rule or something like this, you find that the 0 over 0 gives you something finite. So in the book, I go through the details, and I motivate this a little bit more. I give you more of a story, but I'll just, I'll just leave it at that here. Cut to the conclusion. I can tell you, for example, that the new metric, in terms of Kruskal coordinates, the Schwarzschild metric in terms of Schwarzschild coordinates looks like this. There's a 1 over r factor. There's an exponential factor in r. And there's a d big U, d big V, plus an r squared d theta squared. The only catch here is now we still have r in the metric, but now r has become a function of u and v, right? So that goes back to what we had over here. Before we had r of little u, little v. Now we're going to have r of big U, big V. And while that, that relationship between r and those guys here will be basically imported from what we had before. And just to write down what the answer is, r is now going to be defined implicitly in the following way. So, two things. We've cured the coordinate singularity. So first of all, we've cured the problem of the sequence accumulating up to u, little u goes to infinity on the event horizon. That we've cured by taking this exponential form, and that did the trick. So u now goes to 0 on the event horizon. U can be continued to negative values. And we see a metric here that has a perfectly nice form. Nothing funny goes on at r equals 2m. This goes to 1. This goes to a constant. Something funny happens at r equals 0, but that is where we know the singularity is. And we're not surprised to see something funny going on there. But at least as far as the event horizon is concerned, everything looks well behaved. The only problem is that now it's become, r has become a rather complicated function of u and v. It's still defined implicitly. And that's something that we have to work with when we work with Kruskal coordinates. We have to deal with the difficulty of, inverting this relation to get r as an explicit function of u times v. That equation is interesting. Well, for one thing, we knew this already, but we verified that when r is equal to 2m, u times v must be 0. And this we expected because we've designed the whole thing so that big U would be 0 on the event horizon. But there seems to be another way of making that equal to 0, and that's to say that U could be finite and big V could be 0. That's back to the old situation we had before, which we sort of dismissed before, but now it sort of resurfaces. There's more to it than that. If I want to solve R, if I want to solve this equation, so this structure, this this equation has the structure of some function of R equals the product of U times V. Yep.
Isn't negative U times V equal to 1?
Sorry?
Oh, never mind. Sorry, I was thinking in the same exponential.
Yeah. Sorry, you're fine?
That's fine.
Yeah, okay. Okay, so the structure of this equation is that if I give you R, that gives me a constant, and that constant will be equal to a product of U times V. Suppose that I want to extract, I want to solve for this in terms of U equals something or V equals something. Well, the point is that when you solve this, what you get is a two-branch solution. There's always two solutions for any equation that says R is equal to a constant. For example, if R is equal to 0, if R is equal to 0, this is 1, this is minus 1, U times V has to be equal to 1, and the solution to the equation U times V equals 1, well, has two solutions, right? It's either, well, it's U equals minus V, but it's a two-branch hyperbola in the UV plane. So if I want to draw a picture, I'll draw a picture that looks like this. I'm going to have a U-axis, and I'm going to have a V-axis. So this is the V-axis. This is the U-axis. This is the place where U goes to 0. This is the place where V goes to 0. And we know that this is the place where R is equal to 2m. And now, well, we have to consider the fact that this is also a place where R goes to 2m. But we didn't know about that before. Pretend you didn't know anything about this if you already know something about this. We know about this one. We know that this corresponds to the event horizon. We still don't know what this corresponds to. R equals 0, where R equals 0 is U times V equals 1, so it corresponds to a surface like this. Both U and V can be positive if U times V are equal to plus 1. So that's the place where R is equal to 0. But this is also the place where R is equal to 0, because U and V can both be negative for U times V to be positive. If I pick R to be larger than 2m, say R equals 3m, then this gives me a positive number on the left-hand side, so U times V has to be negative. Where U times V being negative means that, well, U can be negative if V is positive. So that would be a surface R equal constant, say R equals 3m. But another way to arrange this would be to say that U can be positive provided that V is negative. And that would be another description of the surface R equals 3m. So you see what happens, right? So in this construction, every surface where R is larger than 3m has two copies, one on the right, one on the left. And any surface R equals constant below 2m will have one copy here. This would be R equals m. This would be another copy, R equals m. So the construction, the classical coordinates were supposed to achieve one thing. It was supposed to allow us to extend the Schwarzschild metric beyond the event horizon, which in this picture really meant getting an extension across this surface over here. Because so in this in this construction, those are all outgoing light rays that are characterized by U equal constant. Those are all incoming light rays that are characterized by V equal constant. And before we had an accumulation of outgoing light rays at the event horizon, and we can continue beyond that. Now we have the accumulation of light rays at the event horizon, but there's no obstacle in continuing beyond that. So the construction was supposed to achieve this. It was supposed to allow us to go across this surface, but it's given us all of that all at the same time. It's given us 2 copies of each R equal constant surface. And that was pretty surprising. When that first came along, people wondered, okay, what have we done here? What have we done? What is all this? Well, that is the maximally extended Schwarzschild manifold. If you take the pure Schwarzschild spacetime and you don't worry about where the matter is, where the collapse takes place, if you just take the pure Schwarzschild solution and you try to extend it in all possible directions, that's what you get. You get one future horizon here, but you also get a past horizon here. The future horizon has the property that if you're in here, moving inside the light cone, now in this diagram, of course, the light cones are all straight because the light rays are all moving at 45 degrees. That's why I oriented my axes in this direction. So all the light rays are nice and straight everywhere. If you're inside the future horizon, you're stuck in an observer moving, with a speed less than the speed of light. We have to move toward r equals 0, and that's what you see here. But there's also a past horizon, and if you happen to be inside that past horizon, it would be the other way around. A moving observer would have to move with increasing values of r and would not be able to avoid the fate of crossing the past horizon. So an observer here cannot go backwards in time, has to move toward the singularity. An observer down here will have to move out of the singularity. Now we have a new singularity. We had the old singularity up here. Now we have the other copy, which seems to be a past singularity. This was a future singularity. And an observer from this side of the space-time will have to move upwards, forward in time, and will have to cross outward, the past horizon. An observer falling in, cannot go back. An observer coming out cannot go back in. So we basically double up everything. We have surfaces of constant r over here. We have other surfaces of constant r over there. So we get a manifold that's uncomfortably large when we do that. But it is the manifold that corresponds to the Schwarzschild solution where you really extend all possible light rays in all possible directions. That's what you get. So I'll stop here. We'll break for lunch, but I'll come back to that in the afternoon, and I'll just say, okay, of all this, what survives if we consider black holes that are formed by gravitational collapse? We haven't put in the matter in here, so we have to think about putting in the matter. And when we put in the matter, well, we'll recognize that most of this, in fact, goes away. It would be inside the matter where the Schwarzschild solution doesn't apply. And when we do this, we find that this diagram is, in fact, nicely compatible with the previous diagram. We don't have all of this extra stuff. But I'll keep discussing this because there's a lot of nice features that arise from this Kruskal diagram, and it's worthwhile to think about all that. Okay, so I'll see you in the afternoon.